Something extraordinary has happened. After vanishing behind the sun, 3I Atlas has reappeared. And what's being observed now is far more puzzling than anticipated. When it emerged from solar conjunction, telescopes captured it again. And what they saw defies everything we've come to expect from objects arriving from beyond our solar system. The first fresh glimpses came from the Lowell Observatory on Halloween night. It revealed a comet that quite simply shouldn't behave the way it does. According to all we know about interstellar objects, it's an anomaly. While we on Earth were watching and waiting, telescopes at the Discovery Channel telescope in Arizona picked up a faint blur. It was edging up above the northeastern sky. For 8 days, 3I Atlas had been completely obscured. It was hidden behind the sun's overwhelming glare. But now it's returned. And it's what astronomers are uncovering in its wake that's causing a stir. They're not sleeping much. They're not ready to move on. Because the surface of this object, this messenger from another part of the galaxy, is coated with something we've never seen before. Not just dust, not just frozen gases. It's shrouded in a layer of organic compounds, some 15 to 20 meters deep. Then what makes this so astonishing is where those compounds appear to have formed. Not near a warm young star, not in the swirling cloud of a new solar system, but in deep, cold interstellar space. They accumulated over billions of years of solitary drifting between the stars. Just think about that. Every observation we're making, every spectrum we collect, isn't giving us a look at untouched material from a distant planetary system. Instead, it's showing us something shaped by the vast, empty spaces between stars. Something forged not in a cradle of planets, but in the silence of the galaxy itself. We're peering into the past, into a shell sculpted over billions of years by the relentless bombardment of galactic radiation. Long before our own sun ignited, Belgian and American scientists fed the data through computer simulations. And the results overturned much of what we thought we understood about objects from beyond our solar system. These simulations revealed that 3I Atlas has been exposed to cosmic rays for anywhere between 3 and 11 billion years. These rays, hurled across space by exploding stars and colliding black holes, have dug deep into the comet's surface. They fracture simple molecules. They build elaborate carbon structures and then dismantle them again. This cycle has unfolded like a vast interstellar forge, one that's never shut off. But then, things start to drift into unfamiliar territory. The chemical fingerprint of 3I Atlas looks nothing like any comet we've ever examined. Carbon dioxide dominates its emissions. It has 7.6 times more carbon dioxide than water. That alone is striking, since comets are expected to be largely composed of water ice. We think of them as dirty snowballs drifting through space. This one barely fits that picture. Spectral analysis shows elevated carbon monoxide. It shows an unusually red reflection spectrum. This suggests an organic layer envelops its surface. But even that isn't the strangest part. What truly rattles expectations is in the metallic fingerprints. The ratio of nickel to iron matches engineered alloys. It does not match the cosmic dust we typically encounter. Even more startling, the nickel to cyanide ratio is magnitudes higher than any other comet. This includes Borisov, the previous known interstellar visitor. Some scientists now estimate that the odds of all these features occurring naturally are less than 1%. Then there are the polarization measurements. They're not just unusual, they're extreme. The comet displays negative polarization at levels no comet in history has shown. That's not a small deviation. It's a statistical outlier. When light scatters off the cloud of dust and gas surrounding 3I Atlas, it doesn't behave the way it's supposed to. It behaves in a way no existing models can predict. And we haven't even touched on the orbit. It's moving on a retrograde path. Yet, it's aligned within just 5 degrees of the ecliptic. That's the thin plane along which the planets orbit the sun. Its trajectory cuts right through the solar system with uncanny precision. Its wings pass Mars, Venus, and Jupiter. Its closest approach to the sun, its perihelion, occurred at the exact moment Earth was positioned behind the sun, unable to observe. The statistical chance of these events aligning is just 0.2%. Combine the timing and geometry, and the total likelihood drops to 0.005%. Then came July and August. That's when something appeared that bent the laws of physics. Observers reported a jet, an anti-minus tail. It was not trailing away from the sun as we'd expect. It was pointing straight toward it. Not a trick of perspective, but a genuine outflow of material. It was defying known cometary behavior. The PN- reviewed studies are published. The measurements are confirmed, but the physics behind it is still a mystery. And as 3I Atlas drew closer to the Sun on October 29th, Space-based Sumter observatories recorded a sudden explosive brightening. Ist EREO, SOHO, and GOEO, S-19 were watching. It glowed more intensely in certain wavelengths than the Sun itself. Imagine that. A frozen fragmentary interstellar space, reflecting more blue light than our star. But there's something else. Something that excites physicists. This close encounter created an opportunity to test Einstein's general relativity. According to the theory, the Sun's gravity should bend light from 3I Atlas by 0.27 arcseconds per degree of angular separation. It's subtle but measurable. And that's exactly what ALMA, the Comma Large Millimeter Array, detected. The comet appeared for arcseconds from where it should have been. Some of that offset could be due to gravitational lensing. But there's another possibility. One that's even harder to explain. Non-gravitational acceleration. The comet changed speed not because of gravity, but from something else entirely. If that's caused by jets of gas erupting from its surface, it should have shed at least 15% of its mass. That's roughly 5 billion tons of gas and debris. That's not something that can go unnoticed. And now telescopes will continue tracking it through November and December. They will be searching for that enormous cloud. If it's not there, then we're not dealing with one anomaly. We're dealing with a 10th. And right now, across the northern hemisphere, amateur astronomers are turning their telescopes skyward. They are watching this object glide through the dark. 3I Atlas is back from behind the Sun. It is daring us to understand it. It's just a faint blur hovering above the eastern horizon in the soft light of dawn. But that blur is growing bolder by the day. As the comet climbs northward and pulls away from the Sun's glare, the global orchestra of observatories is now joining in. The moment for detailed spectroscopy study has arrived. And with it comes a theory, both enlightening and unsettling. This idea is that 3I Atlas is coated in a crust of organics shaped by galactic radiation. This helps clarify certain riddles. But it also opens the door to others. If energetic particles altered its surface to a depth of 20 meters over billions of years, then, astonishingly, the comet has shed less than a meter of material across most of its journey through our solar system. Perhaps near Perilhana, a few dozen meters boiled away, but only if the object falls within very specific size limits. Either way, we're not examining untouched debris from another stellar nursery. We're looking at something that has been chemically sculpted by cosmic rays. And that leads us to a deeply uncomfortable problem. How can we trace the origin of something when the very skin of the object has been rewritten by time and radiation? Every signature we detect gases, dust, light might be whispering not about where it was born, but about what it has endured. It's been drifting through interstellar space. It's as though we're trying to read a manuscript left exposed on a windowsill for 3 billion years. The words still cling to the page, but the story they tell isn't quite the original. Some scientists are starting to wonder if we've been asking the wrong questions altogether. What if these strange findings aren't isolated quirks? What if they're threads of a deeper pattern we've yet to see? The fact that 3I Atlas passed within 9 degrees of the legendary WAVE signal's origin probably means nothing. Probably, its path carefully navigating planetary gravity assist while remaining awkwardly positioned for clear Earth-based tracking is an oddity, but not impossible. And those industrially weighted metal ratios. The curious polarization behavior. That flare and brightness like nothing we've seen before. Each of these on its own can be rationalized if we stretch enough. But when you add them together, 9 anomalies, maybe 10, depending on upcoming data at some point, the statistics start to groan under the weight. We live in a strange universe. Chaos reigns. Unlikely things happen all the time. But is it normal for so many unlikely things to cluster around a single object? That's why December 19th is circled on every astronomer's calendar. That's when 3I Atlas swings by Earth in its closest approach. Not close enough to raise alarms, but close enough to finally see it clearly. Every major instrument capable of tracking it will be trained on this enigmatic traveler. Spectroscopes, polarimeters, radar arrays if conditions allow. They'll all be working around the clock, because this is a chance that may not come again for generations. After the comet rounded the sun, it began revealing secrets that were hidden during the inbound leg. As the heat works its way inward, layers buried deep begin to give off gases. Every molecule that escapes carries with it clues. Clues about what lies within, about structure, chemistry, and temperature. And so the spectrographs spin into motion. They are peeling apart the light. They are chasing molecular fingerprints in the darkness. Chang Zhong at Lowell Observatory did something remarkable. With nothing more than a 6-inch amateur telescope, he captured an image of 3I Atlas when it's at a mere 16 degrees from the sun. It was just 5 degrees above the horizon. He caught it during that delicate sliver of time at dawn, when the sky is still dark enough and the comet just high enough. If that's what a small scope can do, then what we'll learn from professional arrays may be transformational, because this organic crust, this processed skin of the comet, forces us to rethink everything. When cosmic rays collide with ices and carbon compounds, they doctor chemistry to astonishing depths. Carbon monoxide shifts to carbon dioxide. Water molecules are split apart through radiolysis. Complex organics form, are shattered, and reassemble into new architectures. It's not a single reaction. It's a galactic dance of chemistry playing out over eons. The result is a surface layered with the echoes of that journey. So what does this mean? It means that every interstellar object we encounter might not be wearing its true face. What we see may be a mask of transformations etched by radiation, not birthplace. It's like examining a piece of driftwood and trying to guess the species of the tree it once belonged to after centuries of tumbling through salt and surf. The truth is there, but it's hidden beneath the scars of time. And what unsettles astronomers the most, what keeps them poring over the data in the dead of night, is that the equations don't quite balance. Not if you insist on purely natural causes. Not for all of it. Not all at once. Consider just the path it's taking. It's moving in retrograde. It's skimming so closely to the plane of the ecliptic. It arrived at precisely the moment when multiple planets were lined up to observe, while Earth itself sat at just the wrong angle, unable to see directly. Feed those parameters into an orbital dynamics simulator, and watch the statistical likelihood plummet until it dissolves into the noise floor. Then layer in the composition. There's a concentration of nickel that matches industrial refinement, not the loose mix of natural origins. And for something labeled a comet, the water content is surprisingly minimal. It bends what we thought were universal rules. Any one of these details might stretch the bounds of expectation, but stack them together, and it's no longer a stretch. It's a cascade. Either we're watching probability collapse in on itself, as though the universe has rolled a cosmic die and landed on 6, 9 times in a row, or something else is unfolding. Now, the radiation processing theory, yes, it accounts for certain features. The organic shell makes sense. The dominance of carbon dioxide checks out. Even the red hue in the spectrum fits. But that same theory leaves the nickel abundance hanging unexplained. It doesn't touch the flight path. It doesn't clarify the presence of an anti-minus-tail behaving contrary to solar wind expectations. And it certainly can't account for the light curve spike when the comet reached perihelion. It brightened far beyond any known limits. And it turned bluer than the sun itself. During the critical hours at its closest approach, solar observatories recorded something unprecedented. The intensity of the outburst didn't just stand out. It tore through the statistical norm. It wasn't simply brighter than usual. It was in another category entirely. And that shift towards blue, that unexpected hue, suggests an inequal distribution beyond the bounds of standard sublimation. The established models weren't built for this. So now, whispers are beginning to circulate. Not in official papers or press releases, but in quiet messages, confidential exchanges, hallway conversations after the sessions end. The data are reliable. The readings are consistent. The discrepancies are real. But where that data logically leads, that's the uncomfortable part. Because science builds itself on caution, on deliberate progress, on conclusions tempered by what won't jeopardize a career. To follow this trail to its end requires stepping away from safety. And so a deeper question begins to surface. What if we're framing the whole thing wrong? What if the point isn't whether these peculiarities can be stretched to fit our natural models, but whether we're ready to entertain the possibility that our models need revision? Because scientific progress doesn't come from endless patchwork to old ideas. It begins when someone has the courage to say, "What if we're wrong?" The timing tune feels like something from a cosmic performance. Discovery in July. Highest visibility in August and September. Then an October disappearance behind the sun. Now it's returned in November, with its closest pass due in December. Like a magician unveiling one impossible turn after another, always keeping the final card just out of reach. While sunlight made optical tracking impossible during conjunction, radio telescopes kept watching. Instruments like ALMA continued collecting data. And that for arc-second deviation, just enough to raise eyebrows, catches attention. Some of it, yes, can be attributed to gravitational lensing. The sun's mass bends space-time after all, as Einstein showed so precisely. But only part of the shift is accounted for. The remainder implies an acceleration without an obvious source. And if outgassing is suggested, then where is the plume? 5 billion tons of expelled matter doesn't vanish. It should scatter light. It should paint spectroscopy signatures across the sky. It should leave a visible trail. So these next few weeks, November into December, matter. If we find the debris cloud, we'll have validated extreme but natural cometary behavior. If we don't, then we're dealing with something that breaks away from category, something that requires us to invent new language for what we're seeing. Across the world, amateur astronomers are stepping into the story. Clear skies, low eastern horizons, that's all they need. Star charts marking its position are spreading quietly, handed from one observer to another. People are rising before dawn. They are carrying telescopes into open fields. They are chasing photons that set out from an object forged around a different star billions of years ago. That link between backyard stars and interstellar visitors is intimate, and it matters. Meanwhile, professional teams are mounting coordinated observation campaigns across the spectrum. Optical instruments are charting movements on light curves. Infrared telescopes are reading the warmth and grain of dust. Radio arrays are probing for gases and electromagnetic traces. Ultraviolet sensors are looking for hydrogen and oxygen lines. Even X-ray detectors are tuned for signs of high-energy emissions. Every tool we have is focused on this one object, this puzzle hanging in space. And within that campaign, the gravitational lensing analysis stands out. It's a precise test. General relativity tells us how much light should bend when passing near the sun's gravitational well. The theory offers clean, testable predictions. The question is, how far from those predictions will the data drift? The calculation works out to 0.7 arc-seconds for every degree of angular separation. That's a shift we can actually detect with today's instruments. If this subtle deflection, predicted by general relativity, is buried within the AL in A data and A data, alongside the unexpected deviation in position, then we might be witnessing something quite beautiful. A validation of Einstein's theory using a visitor from beyond our solar system as the proving ground. And now, university departments are scrambling, telescope schedules are shifting, graduate students are submitting urgent observing proposals. Postdocs are staying up late, sifting through streams of raw data. This is the shape of astronomy when the unknown suddenly appears in the sky. The normally measured pace of investigation quickens. Papers that would take months are produced in weeks. The archive overflows with fresh preprints. Conference calls link teams across hemispheres. Because opportunities like this don't come often. At the same time, theorists are feeling the pressure. The existing models don't stretch far enough. You can't just adjust a variable and make all 9 observed anomalies fit comfortably within the framework of classical cometary physics. The models that address the organic surface layer don't account for the orbital peculiarities. Those that explain the comet's backwards minus-facing anti-minus staled and predict the sharp increase in brightness. And the chemical profile that aligns with the spectroscopist data does nothing to address the unexpected polarization. It's as if each solution turns another piece of the puzzle upside down. It's like solving one face of the Rubik's Cube while scrambling the rest. And so some researchers are beginning to take a step back. Their aim is evaluating from the ground up. What assumptions have we made? What priors are we using to interpret this? We've confirmed just 3 interstellar objects, MUA, Borisov, and now 3I Atlas. Statistically, that's a pinprick in the data. We don't know what's typical for these cosmic nomads. Perhaps these extremes are normal, and we've only caught the outliers. Or maybe, just maybe, we've been unusually lucky. And then there's the wow signal. Statistically speaking, the correlation probably means nothing. Radio astronomy has accumulated a long catalogue of unexplained bursts. Given enough time, one of them was bound to coincide with something curious. But still, it's hard to ignore. The trajectory of 3I Atlas comes within 9 degrees of the spot in the sky where that mysterious transmission was recorded. How many times can we call something coincidence before the word starts to feel hollow? Here's what we can say without uncertainty. 3I Atlas is real. It came from interstellar space. And it's behaving in ways that bend the limits of what we understand about comets. This isn't about whether the instruments got it right. Multiple observatories, using different tools and methods, have recorded consistent results. The real challenge is deciding how to interpret them. Just consider its mass and speed. The nucleus is estimated to be about 1 million times heavier than UNUA, and 1,000 times more massive than Borisov. Yet it's moving faster than both. The odds of spotting something with these exact traits less than 0.1%. Add it to the growing list of statistical outliers. And the size. Depending on which observation you trust, the estimate stretches from 220 meters to as large as 2.8 kilometers. That's not a small range. But even the lower bound implies a significant mass. If we take the small end of the estimate and consider that a 29-meter crust of organic coats its surface, then a sizable fraction of this body is material shaped by cosmic radiation across untold epochs. But peel back that processed crust, and what lies beneath? Could it be pristine gneisses from a star system we've never seen? Or is it something entirely outside our catalogue of known materials? Many are focused on the water. Only 4% of the comet's mass is HR. That's startlingly low. Solar system comets usually contain between 60% and 80% water odds. Even factoring in billions of years of radiation damage, the difference is difficult to reconcile. Where did it go? Did it sublime away over the journey through interstellar space? Was it converted into complex carbon-based molecules? Or perhaps was it never present to begin with? Some planetary scientists are beginning to wonder whether 3I Atlas even formed in a typical solar system at all. What if it's a relic of the galaxy's youth? A leftover shard from a time when the chemistry of star formation was vastly different. In that case, the heavy carbon content and complex organic compounds might be the chemical fingerprints of a time long gone, before the galaxy settled into its current rhythm. It's a compelling idea that this subject preserves the ancient, primordial building blocks of matter from the early Milky Way. But even that elegant possibility runs into the same wall: the trajectory. The motion through space doesn't just hint, it shouts. Orbital dynamics is unforgivingly precise. You can't just brush aside the tight alignment with the ecliptic plane. You can't shrug off the geometry of its planetary flybies as coincidence when the math says otherwise. And perhaps most baffling of all, you can't ignore the fact that it reached its closest approach to the Sun exactly during the period when Earth-based optical observations would be most hindered. The way 3I Atlas brightened as it neared perihelion deserves particular attention. Under normal comet behavior, we expect a slow, steady increase in brightness as solar heating causes frozen gases to sublime. But that's not what the instruments aboard DEST, EREO, SOHN, and GOES recorded. Instead, they saw an abrupt surge. A rapid, almost exponential increase in brightness over just a few hours. And came a shift in the color spectrum towards blue. That's a signal that the light being emitted had changed. It was no longer consistent with thermal radiation from dust, simply warmed by sunlight. Energy doesn't emerge from nothing. For 3I Atlas to suddenly brighten and turn bluer, something had to be releasing energy that was either stored internally or converting it from a form we hadn't yet fully grasped. There are standard ideas, of course. Fresh ice could have been expunged all at once, or perhaps the object fragmented dramatically. Both of those events should leave behind signs we can detect. Expanding clouds of debris or an extended coma. That's why continued observations through November are so crucial. They'll show us whether this material is really there. But then there's the crust. A layer 15 to 20 meters thick, composed of organic compounds, saturated with carbon and altered by cosmic radiation for billions of years. This isn't just a dusting, it's a significant barrier. And it raises a simple question: how does anything sublime through such a shield? Our basic model suggests solar heating builds pressure beneath the surface, eventually cracking it and releasing gases. That process should, over time, expose pristine interior material. Yet what we continue to observe on the surface is still this processed organic layer. Either something is rebuilding the crust, or sublimation is happening in a completely different way than we expect. Think about the physics of that layer. Organic materials are excellent thermal insulators. A 20-meter crust should trap heat, blocking most of it before it can reach the volatile ices buried inside. But 3I Atlas still shows pronounced outgassing. One possibility is that the crust has fractures or tunnels, allowing solar heat to reach the subsurface. Another is that energy is being delivered to the interior through mechanisms that don't rely on simple radiation, perhaps conduction through hidden channels, or some unknown process. Whatever the cause, each scenario offers its own set of predictions, and our instruments will be looking for them. And as the anti-minor stale from July and August, still not accounted for. Normally jets of gas and dust get pushed away from the sun by solar radiation and wind, but in this case we saw a jet pointed toward the sun. That requires something different. By their exotic dust properties that somehow make particles fall sunward faster than radiation could repel them, or active propulsion from vents firing on the side facing the sun. Neither explanation quite fits the peculiar structure of the jet that was observed. Now, some teams are exploring the idea of activity beneath the surface. If there are pressurized chambers of volatile ices inside the comet, those could rupture and shoot out material in any direction, unrelated to solar heating. It's reminiscent of terrestrial geysers or the plumes seen erupting from Pluto's surface. This would allow for jets in unexpected directions, but it demands a specific interior arrangement and precise conditions to work. One of the most perplexing features is the polarization data. When light interacts with dust, it produces patterns we can predict based on particle size, shape, and what the dust is made of. But 3I Atlas shows unusually strong negative polarization, far beyond what's been seen in other comets. That suggests the dust here isn't typical silicates or carbon grains. Perhaps radiation has sculpted these particles into novel shapes. Or perhaps the material is fundamentally different. In labs, researchers are simulating cosmic ray bombardment on mixtures of ices and organics to see if they can recreate this effect. If they succeed, it would support natural cosmic processing origin. If they don't, then we're looking at something else entirely influencing the composition of this comet. And then there's the nickel. Specifically, the ratio of nickel to iron in the emissions data. While cosmic dust can naturally contain both elements, the ratios we're detecting in 3I Atlas are closer to engineered alloys than to anything naturally formed. These kinds of ratios are typical of materials designed for strength and durability, not random cosmic leftovers. It's not impossible for natural processes to produce this, but it's certainly odd. A supernova could offer an explanation. During a stellar explosion, different layers forge different elements. So if 3I Atlas originated from a very specific region of supernova ejecta, it could carry this unusual chemistry. And that's something we can test. If this idea holds, then other elements in the comet should also show signatures that don't align with ordinary solar system compositions. All eyes now turn to December 19th. That's when 3I Atlas will make its closest approach, just a 0.4 astronomical units away. Close enough, depending on geometry, to be within reach of radar instruments. And radar could give us what nothing else can: direct insight into the true shape and size of the nucleus. It can penetrate the dusty veil to show us what lies beneath. It's remarkable what we can uncover with radar. Not only can it reveal how fast an object is spinning or what lies on its surface, but crucially, it allows us to measure its reflectivity, its radar beta. And that tells us about what the object is made of and how it's structured. If 3I Atlas is just a strange but natural comet, we'd expect the radar signature to reveal an irregular body, shaped unevenly, with a mix of textures and densities across its surface. That's what happens when you have a dirty snowball built up over time, gradually battered and sculpted by the rigors of space. But if the signal comes back showing something else, something surprisingly symmetrical, or with a degree of uniformity that nature rarely produces well, that would demand a deeper look. Across the globe, ground-based telescopes are preparing to begin spectroscopy campaigns that stretch over several nights. They'll track how the spectral lines shift as the days pass. They'll measure how different gases emerge from the object and change in quantity, and whether those changes link to its distance from the Sun or the timing of its rotation. The idea is to assemble a detailed timeline of the comet's activity, to trace its rhythms, its chemistry, its evolution. These observations will help fill in the blanks, and they'll test the different theories about what 3I Atlas really is. Above the atmosphere, ultraviolet observatories in space have a particularly critical role to play. Hydrogen atoms surrounding comets emit a glow known as Lyman-sulfur, a signature of water, breaking apart under solar radiation. If early estimates are right, and 3I Atlas carries only a tiny fraction of the water we'd expect, then the hydrogen indolent should be significantly smaller than that of the typical comet. Confirming this would not only support the notion that this object is chemically unusual, it would also rule out the possibility that our instruments are being misled by observational artifacts. There's a theory that keeps circulating quietly in back rooms and late-night conversations. Perhaps we're not looking at a whole primordial body at all. Maybe 3I Atlas is a shard, just one piece of something larger that broke apart long ago. In that scenario, the organic crust didn't form on this fragment specifically, but on the original parent object, then cast down when it shattered. And maybe the peculiar composition we're seeing comes from internal layers that weren't ever meant to be exposed. It's a compelling middle-ground idea, strange, but still natural. But breakups usually leave traces. Fragments, trails of dust, jagged asymmetric bodies left behind by the violence. Yet so far, telescopes haven't seen those telltale signs. No debris stream, no companion pieces. And the light curve, the graph of brightness over time, has remained remarkably steady. No sudden spikes or dips that might hint at something falling apart. That said, if the breakup happened not recently but millions of years ago, during the object's lonely voyage across the galaxy, then any siblings it once had are long gone, scattered or erased. That's where time becomes the real enigma. If this object truly spent between 3 and 11 billion years drifting between stars, then it began its journey long before Earth was born. It would predate not just our planet, but most of the planets in our solar system. The organic materials clinging to its surface could be older than life itself. This isn't just frozen ice and rock, it's chemistry from a time before biology, from a galaxy that was dramatically different to the one we inhabit today. So what did that galaxy look like when 3I Atlas set off on its voyage? The Milky Way was younger. Its stars were different. Its composition was more primitive. Heavy elements were less abundant. Stars were forming more rapidly. Supernovae were more frequent. Even the texture of the interstellar medium was different. If this object holds clues from that ancient epoch, if it truly remembers the conditions under which it was born, then it's one of the oldest physical messengers we've ever seen. But there's a contradiction here. Objects that wander the galaxy for billions of years aren't left untouched. They're hit again and again by dust and debris. Micrometeoroids chip away at them, leaving craters, scars, and chemical changes. Radiation alters what the surface looks like, softens some marks, but can't erase all the damage. If this object has indeed traveled for that long, then high-resolution radar scans or close-range imagery should reveal a battered and ancient surface, etched with the passage of time. The way it spins can also tell us something. An object that's been drifting for eons should, by now, have a chaotic rotation. Impacts and subtle forces over billions of years should leave it tumbling in unpredictable ways. But if the light curve reveals a simple, steady spin around one axis, that could point to a more recent event, something that reset its motion, something that gave it a fresh start. If it's stumbling in a complex fashion, that would fit the narrative of an ancient traveler. There's one more part of the story that people hesitate to bring up, but it lingers in every serious conversation: the frequency of interstellar object detections. Environs are far more typical in appearance, perhaps a kind of calibration source, a natural benchmark. Then now 3I Atlas, which arrives wrapped in mysteries, an object whose timing and behavior push against the edges of what we expect. Each one different, each one challenging us in a new way. Together they form a pattern that refuses to be ignored. This is where the conversation turns difficult, perhaps even dangerous. For those who stake their careers on cautious interpretation, to suggest the notion that one of these might be artificial is to invite skepticism, ridicule, and the inevitable pushback, because the evidence doesn't confirm it outright. And if it can't be proven, why raise the possibility? But then, the evidence doesn't unambiguously confirm an natural origin either. And when the number of exceptions begins to mount, the real risk becomes refusing to ask the unthinkable. Science has a playbook for this. There's a protocol and etiquette, especially when the data tugs of foundations. You start with the most conservative interpretations. You highlight the gaps in your knowledge. You reach for phrases like requires additional study, or not explained by existing models. You don't leap to dramatic conclusions. But somewhere, just beneath the surface of the academic language, there's a quiet admission something about this is genuinely odd. Explaining that to the public presents its own difficulties. You can't just say we don't know what it is. You need to strike a delicate balance between transparency and responsibility. No, it's not a threat. No, it's not a collision course. No, we don't know that it was built. But yes, it's exhibiting properties that we can't fully account for. It's genuinely unusual in multiple, independently observable ways. And that alone makes it important. Some argue that we should simply lay everything out. Publish the full data set. Show the light curves, the acceleration profiles, the chemical analyses. Let people see the details, the margins and error, the uncertainty. Others are concerned that fragments of truth can be twisted into whole narratives. That cherry minus picked anomalies will overshadow cautious conclusions. That exaggeration will spread faster than rigor. And already the media coverage illustrates that tension. Some reports focus on the organic crust and its implications for the chemistry of interstellar space. Others lead with sensational headlines about alien probes, relegating the ambiguity to a footnote. The researchers involved walk a tightrope. They work to correct misconceptions while leaving room for the possibility that we may be witnessing something we've never encountered before. Meanwhile, the data keeps coming. Every night that skies are clear, instruments swing toward 3i Atlas. Each new reading adds another piece to the puzzle. Why don't we see the same approach everywhere? Why did MUA accelerate without a sound? Why did Borisov appear so perfectly natural? And now we have 3i Atlas, something in between. Are we seeing missions from different civilizations? Or variations from the same one? Or are most of them natural with just one or two that aren't? It's a confusing data set, a strange mixture. And we're not going to untangle it in November or December. We might not untangle it at all in our generation, but every bit of data matters. Every new observation adds another piece. Each analysis carves away at the uncertainty. It's slow, it's uncertain, and it's thrilling. This is the heart of what it means to be human, to see something mysterious and try patiently to understand it. And for the children watching all this unfold, their universe is going to be different from the one their parents grew up with. Whether 3i Atlas turns out to be natural or artificial, whether we continue to find more objects, or this turns out to be an anomaly, our perception has shifted. We now know that things from other star systems do reach us. The galaxy isn't distant and unreachable, it's dynamic, it's connected, it's part of our environment. And that changes everything about how we imagine our future. For decades, advocates of space exploration have warned that staying on one planet is risky. But if interstellar objects were a regular feature, if some of them might be artifacts, then the logic deepens. If the galaxy is full of wandering bodies, if some of those carry information or intention, if civilizations really do reach beyond their own stars, then so must we, not because we fear them, not because we seek to compete, but because that's what it means to be a civilization that survives, that grows, that learns. The technical barriers are still enormous. Even traveling to nearby stars would demand propulsion systems we haven't yet built. Surviving a journey between the stars requires technologies we've yet to build. But the passage of 3i Atlas through our solar system stands as undeniable evidence that such a crossing can, in fact, be made. Something, whether shaped by nature or by design, has done it. The physics allows for it. And if the laws of the universe permit this, then what has happened once might happen again. That's the lasting significance of 3i Atlas, regardless of what we ultimately discover it to be. It's living proof that the vast, dark space between stars is not impassable. It's a physical confirmation that celestial visitors do arrive from interstellar realms. It's an invitation to reimagine where humanity could go next. And it's a beautiful reminder that the cosmos is richer, stranger, and far more full of surprises than we often allow ourselves to believe. As December 19th draws near, telescopes are already aimed and waiting. Observers have cleared their schedules around the world. Eyes are turning skyward. We don't yet know what the data will reveal, what analyses will take shape, or what final conclusions might be drawn. But the importance of this moment is beyond question. We are standing witness to something incredibly rare, perhaps entirely singular. An object from a distant star system, drifting into our view, presenting us with puzzles we don't yet have the tools to solve. Its behavior resists easy explanations. Its features challenge what we thought we knew. It's offering up riddles we're only just beginning to ask. And right now, there are more questions than there are answers, more unknowns than knowns. And that's exactly what makes this so thrilling. When we find ourselves feeling confident and comfortable, that's often the sign we've stopped learning. But when we're surrounded by uncertainty, by ambiguity that resists resolution, that's when we know we've reached the frontier. That's when we're pushing into places no one's mapped before. And 3i Atlas has brought us to one of those places. What comes next will depend entirely on what we discover, and whether we're willing to let the evidence take us somewhere new, whether we're prepared to follow the data, even if it leads to uncomfortable or astonishing possibilities.